Okay, so, again, just using population vectors that add up to 1,000, and hopefully I did my arithmetic right. In 2 dimensions, you might have a 300, 700. That'd be like a sane dimented, right? Well, we had a problem about sane dimented borderline, right? So we might have 100, 700, 200, okay? Now maybe we got a couple of, borderline sane, borderline demented, sane demented, 4 categories, right? So we could easily have a model where we have 4 dimensions, okay? Now in any of these, clearly we can write down the matrix. Okay, you might have a little trouble with 3 or 4 dimensions, maybe not, okay? But if it's bugs and trees, you could do it too, right? And that's pretty easy, because you get the tri-diagonal matrices. But in all those cases, you could write down the characteristic equation. And if Wolfram alpha allows you to do a long enough matrix, you could let Wolfram alpha figure out the characteristic equation without having to do a 4x4 determinant with lambdas in it, right? Because that'd take a little while, How would you do a 4x4 determinant? Take the top row, first element, throw out the row in the column, leaves you with a 3-dimensional determinant, which you have to evaluate, right? And to do that, of course, you got to break that into 2x2 determinants. And then add everything up and multiply by this number, right? Then minus this number, same thing, plus this number, same thing, minus this number times the same thing, right? So the rule's just the same for any number of dimensions. It's just that the number of calculations gets out of hand real quickly. And as I've said, there are much easier ways to calculate the big determinants. You just do it by adding multiples of rows to rows. To make everything nice and simple, and then you can easily calculate the determinant. You put everything on a diagonal, and that's all you got. You just multiply the diagonal elements. Okay? So if you're doing a 10 by 10, rather than doing 4 million calculations, you do 100 calculations, get the rows where you want them. Now, you don't understand all that, but it's pretty simple if you know how to multiply them. If you know how to add a multiple of an equation to another equation to eliminate a variable, well, the rows just represent the equations. You just add multiples of rows to rows and eliminate numbers in the rows, okay? It's a simple process if you understand elimination, okay? So you can do that in any number of dimensions, right? And if you get into higher dimensions, well, so be it. In an economic model, you might have 20 different categories that transition in different ways, okay? So this is one example. Now, what can you do with these vectors that correspond to what you can do in 2 dimensions? Well, what's the length of this vector? Pythagorean theorem, right? Well, you can prove that the Pythagorean theorem works in 3 dimensions. That's pretty simple. I could write it out very quickly, but you'll encounter it. But it comes down to what? What do you think the length of this vector would be? What's the simplest analogy you could do with this? Right? That's very simple, okay? Here, well, it's pretty clear what the pattern would be. Okay? So now you've got a definition of length in 4 dimensions, okay? So it turns out space-time is 4-dimensional, so it's real handy to have these kind of dimensions, these kind of definitions in 4 dimensions, right? And I won't get into how you interpret space-time, but it's just matrices, and combined with calculus, and you get tensors, and then it gets really hard, to the point where Einstein sat mostly in his room drinking German beer, eating Polish sausage for 10 years until he figured out all the mathematics and came up with general relativity, which is one of the great intellectual achievements of humanity. amazing. And then he lucked out. Like 2 years later, they did some astronomical observations that relied on the clouds parting at just the right time, and they did, even though it was really cloudy. And he got measurements that showed that light bends as it goes around the sun, just as he predicted. Okay? Pretty astounding. Then he became world famous instantly. Okay? And that's all because of German beer and Polish sausage or whatever he was eating. Okay? Yeah?
So the length you're finding right there is the length of the diagonal.
It would be.
Okay.
And in 3 dimensions, it's like you have 100 this way and let's say 700 this way, right? But then you've got another dimension that comes out 200 in this direction, so you have the rectangular box here, and it's just the diagonal that goes from here up to here. I'm sorry, up to here. So it kind of looks like it's almost parallel to this one, but if you start here, go this far, and then go this far, that's where you end up, right? And this distance is this. And it's easy to see that because, for example, if you go this far and then this far, then you've got a vector here, right? And then from here up to here is another right triangle. And you just apply the Pythagorean theorem again, and this is it. Okay? And then you find that anything you do in higher dimensions, you divide the magnitude this way, and everything behaves very similar to the way it behaves in 3-dimensional space, even though you can't visualize it. Okay? So, you know, that's a pretty easy extension. So if you understand 2 dimensions, well, there are things that happen in 3 dimensions that don't happen in 2. But there's not much that happens in higher dimensions that doesn't happen in 3. It's just you can't visualize it. Okay? Now, one example in 2 dimensions. Okay? If you have a transformation that rotates everything, there are no eigenvectors, no eigenvalues. You do a rotation matrix and try to find the eigenvalues, they're all complex. You get an I, you know, it's square root of -1 when you try to solve for lambda, okay? But you can still do that. Matter of fact, the matrix is just like the sine, the cosine, negative cosine, sine, those are your 4, and that rotates everything through angle theta, right? Through whatever angle you want. And I think I said those in the wrong order because I'm not thinking about it, but it's simple to figure that out, okay? So, well, that's pretty simple. You know, you rotate it this far or you rotate it this far. There's really not much choice. You're going to rotate at some angle between 0 and 2 pi radians, or 360 degrees, right? Mm-hmm. So whatever picture you have just gets rotated. And maybe it gets rotated and expanded. You can do that too. Just simple linear matrix, okay? Simple 2 by 2 matrix. And you can figure all that out, and that's pretty easy. Okay? You go into 3 dimensions, and now instead of a circle, you've got a sphere, so you can rotate this way, or you can rotate about this axis. You can rotate about any axis in 3-dimensional space, and you can't do that in 2-dimensional space, right? Well, there's a mathematical object called a group, which is something, you know, I could teach you about in an hour. I mean, you know, just about, say, rotation group in 2 dimensions. And very simple, okay? But in 3 dimensions, it becomes incredibly complex because of all the ways you can rotate things. And how does this rotation combine with this rotation, and what matrix would you use for this one and this one, and how do you combine the matrices to get the net rotation, and all of that stuff, okay? So you can have a 500-page textbook on rotation groups in 3 dimensions and not be able to understand a word of it, okay? So, you know, things get very complicated very quickly. And then you go up to 4, 5, 6 dimensions, and then it gets harder, but not that much. Okay. 3 dimensions is kind of unique. There was a millennium problem, I think. And it just deals with the nature of a sphere in four-dimensional space. Now, a sphere in four-dimensional space is three-dimensional, just like a sphere in three-dimensional space has a two-dimensional surface. You take the surface of that sphere, slice it, flatten it out, right? So it's really just two-dimensional. Like we're walking on the surface of a sphere right now. We did perceive this surface as two-dimensional because it is, okay? Well, you embed a three-dimensional sphere in four-dimensional space, basically. Call that the three-sphere. And there was a conjecture about the topology of the three-sphere. You could prove it for the four-sphere. You could prove it for any dimension above 3 and any dimension below 3. But nobody could figure it out for 3. Until a Russian mathematician, I'll probably butcher his name, but it's P-E-R-E-L-E-M-A-N, Perelman, okay? Or Perelman, I don't know. And I don't know how it's pronounced in Russian, okay? But I could ask my former son-in-law, who's Russian, and extraordinarily well-educated, really. But he would be able to tell me at least how they pronounce it in Moscow, but that's not how they pronounce it in St. Petersburg. You know. So, you know, anyhow, that's beside the point. And he solved it. So I said, oh, okay, here, come on here and get your $1 million prize, because that's what it's worth. Okay? He said, no, I do mathematics for the purity of mathematics. I don't want your money. That's pretty pure mathematician. I mean, he's making a living. You know, he's getting paid. He's not starving. But $1 million is $1 million, and it's more than he's getting paid. Okay? But that would tarnish the purity of his mathematics, as best I can interpret what I think he said, what's been reported that he said, and what I remember about it. Okay? Kind of interesting.